The charts? Okay. Oh yeah, okay. Right, so we talked about activators versus deactivators. So there's on a benzene, like each substituent is classified as two things. So the first thing you have to decide if it's an activator or a deactivator. And then the second thing you have to classify is like what carbon it's going to direct to. So whether it's an activator or deactivator and what carbon on the benzene is it going to direct to, ortho, meta, or para. So we have to consider both of those. So like for an alcohol, is it an activator or deactivator? And what carbons do you think it directs to? Yes. Like what, if you have an electrophile, like if you're reacting a phenol with an electrophile, what carbons is the electrophile going to get added onto? So we call alcohols OP directors because they're going to direct new electrophiles to come onto ortho and para. So usually activators, I think almost all activators are ortho para directors. So on the chart, you see all your activators, just know that whenever they are in a reaction, the electrophile goes ortho para. So you can see that here in this lovely little chart, we have our activating groups, which are all of these, and all of the activating groups are under ortho para directors. And then the deactivating groups are all of these down here. So the halogen and all of these strong deactivators. So the strong deactivators are all meta directors. So they're all going to put new electrophiles on meta. The only exception for the deactivators is the halogen. So halogens are weak deactivators, and they direct ortho and para. So they're weak directors, and they're also OP directors. This is because like the halogen resonance works the same way as the activating groups. Like it's kind of annoying to draw out, but just know that it's because the X resonance and like, for example, like the OH resonance would basically be the same. But there's two things with the halogen. So it has an inductive effect, which means it like sucks electron density out of the benzene, but also by resonance, it donates. So there's like two contrasting effects. There's one where you're pulling electrons and one where you're giving electrons. So it kind of like ends up being a weak deactivator that directs ortho para. Okay, so this is important. This is the order of reactivity. So this is going from most reactive to least reactive. So for most reactive, you have your NH2, it goes all the way to NO2. The most reactive benzene, this like aniline, is going to react the fastest. And then this NO2 is going to have the slowest reaction time. So the other thing that's important here is that if you have two activators on a benzene or two substituents on a benzene, you're going to wonder, okay, which one is going to have like the major directing effect? So which one is going to be responsible for the final product? So I don't know, let me give you an example. Okay, let's take one from here. So let's take benzene number 4. We have two substituents on there, right? So the one on top, this amide, where is it going to direct? Which carbons? Yeah, so the amide is going to direct to ortho and para because it's an activator. So the amide is encouraging the electrophile to go to those carbons. And then what about the methyl? Where's the methyl directing? Oh, this was a bad example. Okay, so the methyl is an R group, which is an ortho-para director. So this methyl is also directing ortho-para, which happens to be the exact same carbons. So this example sucks. Okay, but there's something we can get out of this. So in the final product, this is going to be your final product. You're going to have a mix of two. So we're going to put whatever electrophile on these two carbons. Why wouldn't we put it on this third carbon over here? Exactly. So you never really put an electrophile between two substituents because of sterics. So if two substituents are meta to each other, you're not really going to add an electrophile in between them. It's not favorable. So in our final product, we just have the product where the electrophile is ortho to the N, and then one where it's ortho to the methyl. Okay, so number 5 is a better example. So for this fifth benzene over here, where is the SH directing? Which carbons? Ortho and para. So this SH wants the electrophile to go to those 3 carbons. And what about the SO3H? SO3H wants it to go meta. So that would be this carbon only. We can't really do the, we can't really count the SH carbon because there's already something on it. So we can't add anything else. So the SO3H is only really directing to one meta carbon. So like which carbons is the electrophile going to get added to? The meta or the ortho-para ones? Well, would it be meta? Why would it be ortho-para? Exactly. So those ortho-para carbons are more reactive. By more reactive, we mean more electron density. So it's more willing to like bond to the electrophile. So the ortho-para carbons are much better to put an electrophile on because the SH is more reactive. In our final product, we're going to have one with the electrophile. So one where the electrophile is going to be para to the SH, and one where it's going to be ortho to the SH. We're not really going to have much of a meta product. So every time you have a benzene with 2 substituents that have like competing directing effects, like they don't overlap like they do in benzene 4. So when you have competing directing effects, you have to go to this chart and see which one is more reactive. So the one, like the substituent that's further to the left, is going to have higher priority. So in this case, we are comparing SH versus SO3H. So SH is not here, great. Okay, so SH is somewhere like around the alcohol because sulfur functions like alcohol. So yeah, so SH is there because it's like pretty strong resonance activator. While SO3H is all the way down here, it's a strong EWG. It's really not reactive. So SH being an activator and SO3H being a meta deactivator means that SH automatically like wins priority. Okay, so what about this question? Out of these 5 benzenes, which one would be the most reactive towards an EAS? It would be 4, because I think 4 is the only one that has, so 4 has no EDGs, so it has no deactivators. It has only activators, and it also has the N. So the N is a resonance activator, which means it's like pretty strong, and the methyl is an induction activator, so it's weaker. Probably not. Yeah, because that really is bad. Okay, so from the methyl, we see on the reactivity chart that it's all the way down here. It's like the least reactive activator. But the NH, the amide, is like medium reactive. So the amide and the methyl is good. In benzene 3, we just have 2 R groups. So we have 2 of the weakest activators. So that is going to be weaker than benzene 4. Okay, and then which of these 5 would be the least reactive? Four again, yeah. So 4 is the only one that has a strong deactivator, a strong EWG on it. So yeah, it's the least reactive. And then we have 2 benzenes with esters. The difference is that they're connected differently. So on benzene 4, the benzene is connected directly to the carbonyl carbon, which means that resonance is going out of the benzene, it's withdrawing. And then for benzene 2, it's connected to the oxygen. So oxygen has lone pairs, and it's going to donate those lone pairs into the benzene through resonance. So EDG, EWG. And then which one is going to be the most reactive here? The NH2. NH2 is like the most reactive substituent. This is the last page. Damn, okay. So yeah, there's a reaction. What reaction is it? And then what do you think the final product would be? What? The right side, or, oh, so like these? Okay. Well, don't say that. So what reaction is it, first of all? What are we adding? Nitration. So we're adding NO2. And then we have one vote for the ortho and para carbons over here. Okay. Do we all second and third and fourth that? No? Okay. Okay, who's fourth? Okay, I'm fifth then. I think that's right. So we're just gonna compare the directing effects. So the methyl is directing ortho and para. Methyl is wanting the NO2 to go to those carbons, except not this carbon because of steric hindrance. So it's directing to those 2 carbons. And then this carbonyl over here is directing meta. It can't direct meta on the methyl because there's already some stuff there. So that carbonyl is directing to that meta carbon. So now which substituent is stronger, the methyl or the carbonyl? The methyl is stronger, it's more reactive, so the methyl is going to have priority. So because the methyl is more reactive, we're going to add the NO2 onto like the pink carbons. We're just going to like ignore what the carbonyl wants. So the NO2 is going to go here. And it's also going to go here. So ortho and para to the methyl. Did Wes ever like talk about major, minor, or like he doesn't care? Okay, good. So in this case, like the first product would probably be a bit more major because of sterics, but like functionally the same amount, I guess. Okay, so we have a 2-benzene thing now. Yeah.
What the one on the meta show? Like what it is like a small.
Oh, maybe like 1%. Yeah. So on this 2-benzene thing, what do we think is going to happen? How do you know that? Okay, yeah, but why is there no product on the left side? Uh-huh. But you're answering, so. Sorry, say that again.
Would it have to sell off the NH? The methyl?
Yeah, it would have to go onto the NH side. So in these cases, I just like cut it in half. So I see that the left benzene is attached. The left benzene is attached to the carbonyl. So the carbonyl is a strong EWG, and it deactivates reactions. So we're not really going to add to the left benzene because it has to deal with that carbonyl. But the right benzene is attached to the NH portion of the amide. So if you remember, the NH side is an ortho para activator because it has the lone pair. So lone pair is going to go there and like activate it ortho and para. The other thing here is that like this reaction, what is it called? Related to the carbonyl. Alkylation. So this is Friedel-Crafts alkylation. If you remember, one of the big limitations of Friedel-Crafts is that you can't do it when there's a strong EWG there. So it doesn't happen on benzenes that are connected to a strong EWG. So it's not going to happen at all on the left because the carbonyl is strong withdrawing. So like maybe with another EAS, you would get like minor product on the left, but for Friedel-Crafts, you won't get it at all. Anyways, let's draw the product. So the NH we said was ortho-para directing. So those are the ortho-para carbons to it. And then we just slap on the methyl. So you get 2 products. You get one where the, oh, actually 3. Wait, no, it's the same. So you have one methyl ortho and then another methyl para. And like these 2 ortho carbons are the same because of free rotation. And how do we know that we were adding a methyl here? Like in the final product, I added a methyl, but like, where did that come from? CH3Cl. So remember in Friedel-Crafts, you have the AlCl3 that just cuts off the Cl and replaces it with the carbocation. So our reactive species, our electrophile in this reaction is the CH3, wait, CH3, yeah, CH3 plus. Okay, so what are our thoughts on the next one? Yeah,
Is it halogenation?
so you have AlCl3 and a Cl. So
Or is it MC alkylation?
yes, it is
Is it
Friedel-Crafts.
because of the double bonded oxygen?
Yes, so whenever you see the carbonyl and the halogen, aka the acyl halide, and AlCl3, so carbonyl plus chlorine plus AlCl3, automatically we're doing an acylation. This is Friedel-Crafts acylation. So what are we adding to the benzene, and then where are we going to add it? So we'd be adding it to the right side, right?
It's a para, right?
Yes, but there's two R groups, so orthopara to what? Actually, wait, let me think.
The methyl is more reactive.
Yeah, what? Yeah, but we're looking at the right side, which has two R groups. So like this whole thing on the left is considered an R group substituent of this benzene.
Okay.
It would not.
To the bottom more
Yeah, so like these. Mhm. Yeah, so we're gonna ignore the left side because the left side has an NO2 on it. NO2 automatically deactivates Friedel-Crafts reactions. So we're gonna look at the right side of the benzene. So on the right side, we have to consider two directors. So we have this R group. The whole thing counts as an R group activator. So this is activating orthopara. And then this methyl is also activating orthopara because it's also R. So this methyl is going here and here and here. But we eliminate this carbon because it's in between two substituents and we don't really add there. So both of these R groups, they direct to the same two carbons. So we're just gonna have two products with the electrophile added there. But what is the electrophile that we're adding? The carbonyl, yeah. So remember, the Cl is part of the mechanism. The Cl gets cut off by the AlCl3 and turns into a cation. So this is what's actually doing the reaction, this cation. Whoa. Okay, so the next one, what do we think? It would, and what halogen are you adding? BR, yeah. And where's it gonna go? Meta to which one? Okay. You're right, it's meta. So the directing effects for this, these are both meta directors. So they're both deactivators, both EWGs, they're both direct meta. So the NO2 is directing here, not really this one because there's already stuff there. So this carbonyl is also a meta director, so it's also directing there. And it's not gonna direct to this carbon because there's already stuff there. So both of the metas are pointing towards the same carbon. So we only have one option here.
In this scenario, would the red one be like very, would it have like a kind of like a small U because it's less reactive than the green one? Does that make sense?
Yeah, so like if these weren't, if they didn't align to the same carbon, then you'd probably prioritize the carbonyl bit. Okay, so what about the next one? You're right, sulfonation. And where's the sulfonyl gonna go? Orthopara to, yeah. So what is the CHO? What is CHO and where is it directing? Yes, so it's directing meta. Yeah, so NH2 is like the strongest possible activator, so it's always gonna have priority. So the NH2 is directing orthopara, and then the CHO is directing just meta, which should be here. So that is contrasting, but because we have NH2, like that's automatically gonna win priority. So we're just gonna ignore the meta carbon and then just add an orthopara to the NH2. So our SO3H goes on these two carbons. All right, the last reaction. What do we think is gonna happen?
You have the the craft one, that's when it cuts off the.
Mhm.
last part, okay.
Um, okay, I won't confirm or deny. Any other thoughts? Meta. So what reaction is this? Yeah, Friedel-Crafts alkylation. So does that change anything?
Wait, how is this an activation?
Alkylation.
Okay.
Does it being Friedel-Crafts change anything? Yes. Where you cut it is whatever. Like we know the steel is gonna leave a carbocation. Maybe it'll go secondary, who knows? But let's look at the other thing. Let's look at this benzene. Anything fishy about that? Huh? Yes, no reaction. Why not? Exactly. So anytime you have a strong meta deactivator, EWG, whatever you want to call it, Friedel-Crafts won't happen. So the CN is a strong EWG. Any meta director is going to be a strong deactivator, strong EWG. So anytime you have a meta director, you cannot do Friedel-Crafts. Okay. Oh, there's two more. So for the second to last one, I'm asking you what order, like which reagents you would use and in what order to do this reaction. So like two reactions happened here because we started from a plain benzene and we ended with a benzene with a methyl and also a carbonyl on it. So two additions happened. Which two happened and then in which order? First of all, which two additions happened? Like what two reactions? And so we know we have alkylation and we also have acylation. So both reactions happened. So which came first? And how do you know that? Exactly. So with alkylation, we would be adding this methyl. This methyl is an ortho para director. Our second carbonyl got added ortho, which means that it was directed ortho. So if we look at the acylation, this carbonyl is a meta director. There's nothing on the meta carbons, which means that the acylation could not have happened first because there's nothing on meta. Also, the other thing, we're dealing with Friedel-Crafts, right? What kind of deactivator is a carbonyl? What kind, weak or strong? Other one? Yes, it's strong. So all meta directors are strong deactivators. So carbonyl is a meta director, so it's strong. Any meta director is going to cancel Friedel Crafts. It's going to make it like not happen. So if we started with the acylation first, like if we just started by putting the carbonyl there, there's no possible way that we could have done the alkylation second, because these are both Friedel Crafts. If we did the carbonyl first, the benzene would be deactivated and we can't do any more Friedel Crafts. So there's no way we could have added the methyl on second anyways. If that makes sense. Okay, so we said that alkylation came first and acylation came second. Now, what are the reagents for alkylation? Yes, so we are going to use AlCl3. And what else? Exactly, that's perfect. So we're going to have AlCl3, and in the final product, we added on a methyl. So our electrophilic species was probably CH3Cl3. Sorry, CH3Cl. Because remember, in the mechanism, the AlCl3 cuts off the Cl, and then you get a CH3 cation, which glues itself to the benzene. So what are the reagents for reaction number 2, the acylation? Acyl halide. Yeah. So basically all you have to do, like in acylation, you take your acyl halide. What happens is that the Cl basically just gets replaced with the benzene. So the Cl, you cut it off and you kind of just like replace it with the benzene. So if you're going backwards, you just replace like this entire benzene with a Cl, and that's how you get your starting thing. So yeah, our acyl group was this. So we slap a chlorine on there and we get our reagent. Okay, so what about reaction sequence number 2? What reactions did we even do here? Sulfonation and what else? Sulfonation and halogenation. So in what order? How do you know? Okay, so we knew it's sulfonation because the chlorine got added on meta. So if you look at the SO3H, the SO3H directs meta. The Cl, all halogens are ortho-para directors. So the Cl was directing to those 3 carbons. The ortho-para carbons are completely empty. There's nothing that got added there. So the Cl had to be added second. If we did the Cl first, then the SO3H would be on an ortho or para carbon, but it's not. So we said sulfonation first. What are the reactions for reagents for sulfonation? Our reagents? H2SO4, yeah. So reagents for sulfonation are always SO3 over H2SO4. So that's our step 1. And then what are the reagents for step 2? Mhm.
over FeCO3.
Yeah, exactly. Okay, so that's the handout. We have 6 minutes left. We can either, it's up to you. We can stop here and just like quit, or we can, I don't know, start the practice problems from 15 from Canvas. Yeah. Okay, 4 minutes. Let's go. Yes, I will. If I don't, please like just spam email, remind me. That's the only way I remember. I think it's just, there's one for 15. Wait, what? There's answers? That's so lame. Okay. But I did the one without answers. They both have the answers. Okay, well, we just have to be academically into integritous. I don't know. So, okay, so we all know the answer. So what is the right determining step? Okay, so yeah, what's the answer to this? And why? I warned you about this exact one though. Yeah.
So like the main thing you look at is for the uranium ion, right?
Yes, or it's determining.
Words, like exactly.
Ignore the words, but not the important ones. So what you notice here is that it's asking for rate determining stuff. And then like by rate determining, you can automatically just know that rate determining equals formation of iridium ion. So now I go in the answer choice and pick whichever one is the formation of the iridium ion. So A does not include the ion, so no. B doesn't include the ion either. C has an ion, but it's the wrong one. It's not iridium. D is addition of whatever to produce the iridium ion. That's really good. We like that. And then E is loss of proton by iridium ion to form nitrobenzene. So it's not E because we're not forming the iridium ion. It has to be D. Yeah, so just look for like whatever you know. Number 3. Is it C? Yes. So every EAS, the bromination / chlorination is a type of electrophilic aromatic substitution. All of those reactions require a Lewis acid. So all EAS needs a Lewis acid catalyst. So that would be C. The rest is just like junk because when did we ever talk about that stuff in chapter 15? Okay, number 4. Okay, any other opinions? What about 4? No, like option benzene 4.
Oh,
Yeah.
okay.
Because you said that even though in your low product, it should still happen at like 1%. The chlorine on the meta. Chlorine and bromine.
Oh, yeah, so it's meta to the chlorine and also, wait, no, but chlorine is orthopara.
Oh, what about 5 then? Sorry.
Yeah, not 5. Because the expected product is the major one. We don't care about like the 1%.
Okay.
So with both 4 and 3, the bromine is ortho to the NH2, which is what we wanted. So what the hell? This is 2? Why would you add twice? Okay, so maybe the NH2 is so reactive that you just go ahead and add it twice. That is very sus. I feel like it could be 4 as well.
I just took it as,
Did he show you that like in his little PowerPoint thing?
So I think that was.
So-
that was probably like 2 answers then. I
Yeah,
don't
it would be
know.
both are possible because it would, I think it's mostly 4 with like some 2. I don't know. Okay, so on that note, we'll end it for today. And we'll start 16 on Wednesday. I'll email you the handout tonight.
you only get